Welcome to the video lecture for section 12.1. This is for MSc 1105, College Algebra. My name is Jorge Young. And as you can see, we have 7 objectives, and we're going to go ahead and cover all 7. We're also going to introduce how to solve a system of equations by graphing, and that's the first thing that we're going to do. And so here we have 3 images. We have A, B, and C. In A, we have a system that is consistent and independent. So in a system of equations, you have 2 equations with 2 unknowns. So 2 equations each have an x and a y. If we were to graph them and they intersect at one point, then that system has one solution. For B, this is an inconsistent system. And so if we were to graph these 2 lines, we notice that they're parallel. So that's a parallel line. So the system has no solution. And then for C, it's consistent and independent because the 2 equations are the same equation or same line. And so this has what we call infinitely many solutions. So when we have a system of equations, we either have one solution, no solutions, or infinitely many solutions. So the first example is we're going to go ahead and graph this. And so here's a system of equations with 2 unknowns. We label them equation 1 and 2, and that's going to be helpful as we get into elimination and substitution, and then 3 equations with 3 unknowns. So what we do here for the first one, we solve for y. This is equivalent to writing equation 1 as y is equal to negative 2x minus 1. We graph both equations, and then we can clearly see that they intersect, and then the point of intersection would be the solution to the system of equations. The next objective is we're going to solve the system equation by substitution. So here we have a system of equations with 2 unknowns, 2 equations and 2 unknowns. We have equation 1 and equation 2. And so step 1, what we do is we pick one of the equations and solve for one of the variables in terms of the remaining variables. The easiest thing to do is choose an equation that has a variable that has a coefficient of 1. In this example, equation 1 has a y, and so we're going to solve for y. In step 2, we're going to substitute the result into the second equation. So we know that from step 1 that y is equal to negative 2x minus 1. We're going to replace y in the second equation with negative 2x minus 1. And in step 3, we're going to go ahead and solve for x. In this example, we get that x is equal to negative 3. We're going to take that information and plug it back into equation 1 in order to get our y. When we do that, we get y is equal to 5. So the potential solution to the system in this case is negative 3, 5, the ordered pair negative 3, 5. So what we do is, since we know that it works in equation 1, we verify it in equation 2, and then if it solves both equations, we get a true statement, and the solution to the system in this example will be negative 3, 5. The next example, we're going to solve system of equations by elimination. So some of the rules: interchange any 2 equations in the system, multiply or divide each side of the equation by its same non-zero constant, and then replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. So here we have a system. We have equation 1 and 2. We're going to solve this by elimination. So in step 1, we multiply equation 2 by 2, and so we get the new equation, which becomes negative 2x plus 2y is equal to negative 6. So we can see here in this step right here. Step 2, we're going to go ahead and add the equations. When we add the equations, our x variables cancel out, and then we can solve for y. So we're left with y is equal to negative 1. We take that information, we plug it back in for step 3 into equation number 1, and we get our x coordinate. So in this example, x is equal to 2 and y is equal to negative 1. Now we know that this ordered pair works for equation 1. We check it in equation 2. If it works, we get a true statement. Then the solution to the system is the ordered pair 2, negative 1. Here's an example. Movie theater sells tickets for $8 each, with seniors receiving a discount of $2. One evening, the theater sold 525 tickets and took in $3,580 in revenue. How many types of each ticket were sold? So x represents the number of tickets sold at $8. Y is the number of tickets sold at $6. Discounted price is $6. So we know that the number of tickets was 525. So x plus y is 525. 8x plus 6y is equal to 3,580. So we're going to use the system. We're going to use elimination to solve this equation. So we multiply the second equation by negative 6, and then we add the equations. When we do that, we eliminate the y variables, and then we get that x is equal to 215. We go ahead and plug it back into either of the 2 equations and solve for y. We get that y is equal to 310. So we sold 215 non-discounted tickets and 310 senior tickets were sold. Here we're going to identify inconsistent systems of equations containing 2 variables. So here we have again a system of equations. We got equation 1, equation 2. And so we're going to use the method of substitution. So here we got 2x plus y is equal to 5. We solve for y. Y is equal to negative 2x plus 5. That's from equation 1. We take that expression, this is the right side of the equation, we substitute into equation 2, and we solve for x. And then when we do that, we get that 0 is equal to negative 2. This is obviously a false statement, so we're going to conclude that the system has no solution and therefore is inconsistent. If we were to graph the lines, we find out that they're in fact parallel lines. Next thing we're going to do is express the solution of a system of dependent equations containing two variables. So here we have a system of equation 1 and equation 2. And so we're going to choose the method of elimination. And so here's our original system. We're going to multiply equation 1 by 3. When we do that, and then we add, we get that 0 is equal to 0. This is a true statement. So when we get something like that, 0 is equal to 0, 5 is equal to 5, y is equal to y, an identity, that simply means that they are the same equation. And so if we were to graph them, we just get one line. And so that's infinitely many solutions. Next thing, we're going to solve systems of three equations containing three variables. And so we have A, B, and C. A is a consistent system, one solution. Each one of these planes represents one of the equations. B is a consistent system, infinite number of solutions, sorry. And then so the solutions would be in this plane. C, this is an inconsistent system, no solution because the three planes do not intersect at the same time. Now here we have, we're going to solve this. We have three variables. We have equations 1, 2, and 3. And so what we do here is seem a little bit convoluted, but we can actually solve these using just two equations at a time. And what that's going to allow us to do is eliminate one of the variables for each of the equations. So in the first example, we're going to multiply equation 1 by negative 4. And then so this is what we end up with. If we add those equations, we get negative 7y plus 6z is equal to 20. So we're going to replace this new equation with equation 2 in the original. And then we're also going to have equation 1 multiplied by negative 2. We're going to add it to equation 3, and then we're going to go ahead and replace that. So now we have this system of equations. So we're going to concentrate on new equations 2 and 3. We're going to treat them as a system of two equations containing two variables. And easiest is to multiply z, right, to eliminate z. So in this case, since this is the system that we have, we're going to go ahead and eliminate z. We're going to multiply equation 3 by 6. And then you can see that c is eliminated, so we get y. So here we get negative 31y is equal to 62. Now, at that point in time, of course, we're going to solve equation 3 for y by dividing both sides by negative 31. We get that y is equal to negative 2. Since y is equal to negative 2, we can take that information and plug it back into equation 2. Solve for z, so we get z is equal to 1. And then we're going to finally back substitute y and z into equation 1 to solve for x. And we get that x is equal to 2. Now, the solution of the original system is x is equal to 2, y is equal to negative 2, z is equal to 1, or the ordered pair, which is a triplet, 2, negative 2, 1. And then we check these values in all three of the original equations to make sure it works. Next thing is we're going to identify inconsistent system of equations containing three variables. So here again we have equations 1, 2, and 3. So we're going to use equation 1 and 2. We're going to multiply equation 1 by negative 1. We're going to get a new equation 2, which is negative x plus y is equal to negative 7. And then we're going to take equation 2 and 3 and simply add those, right? And that's going to eliminate our z, and then we're going to put that back there. So here we eliminated z in equation 2, and we eliminated z in equation 3. So now that we have this, we're going to multiply equation 2 by 2 to eliminate, and then we get 0 is equal to negative 22. We put that information there. Equation 3 has no solution, so this is an inconsistent system. Next thing, we're going to express a solution of a system of dependent equations containing three variables. So here we have equations 1, 2, and 3. In this example, we're going to take equation 1 multiplied by negative 2, add it to equation 2 to get the new equation number 2, which is y plus 3z is equal to 7. Then we're going to take equation 1 multiplied by negative 4, add it to 3 to get the new equation 3, which is 3y plus 9z is equal to 21. You can see here now this is the system of equations that we're going to be working with. So now we're going to use 2 and 3 to eliminate one of the two variables. So we take equation 2 multiplied by negative 3, add those equations together, and we get that 0 is equal to 0. So the original system is equivalent to a system containing two equations. So the equations are dependent. The system has infinitely many solutions. And so in this case here, it really means that any triplet of x, y, and z should solve all three because it's the same equation three times. And that's the end of 12.1. Thank you.